be here. So I'm going to talk about using AR and VR for brain synchronization. So many of you, if you've been on the show floor, you'll see companies now are starting to put EEG into their head-mount displays. So there's a company, Neurable, who's here showing a demo upstairs, and Lucid, who's showing a demo next door. And so Neurable, for example, has 6 electrodes at the back of the head. Lucid has 6 electrodes in the frontal lobe. And people are also starting to explore how you can use a higher number of electrodes in conjunction with AR and VR displays. So there's generally 3 different ways people look at it. One is to use the electrodes to measure brain activity to provide a brain-computer interface. So you can concentrate and think, and you can activate menus or something in VR. And most people are working in this space. Some people are also using it for emotion or cognitive monitoring, so you can measure people's stress or workload. And there's been some work, although not yet in the AR VR space, about looking at how you can use EEG to enhance collaboration. And so for those of you who aren't that familiar with EEG, when you wear the electrodes on your head, you can measure the electrical activity of the brain, and that generally falls into 5 categories. And you can see on the right-hand side, you basically measure signals with different frequencies from delta all the way to a gamma. And you know, delta is really associated with sleep, theta with when you're in a tired state, alpha is when you're relaxed, beta when you're alert, and gamma is when you're very, very aware. So from these electrodes, you can measure a variety of signals, and then they decompose into these types of frequency domains as well. So as I said, many people have been working using electrodes to measure, or EEG to measure brain activity for brain-computer interfaces. So, for example, controlling devices by thought, training people to build a trained response, or to provide some sort of hands-free interaction. So here's a nice demonstration of this. If I can plug to the next slide. Okay, great. So this is from a French research consortium called Clara. And in this case, they're using a HoloLens with a very low-cost brain-computer interface. They're using the Muse system, which has 4 electrodes across the front of the head, and this measures the alpha activity in the brain. And it's really inexpensive, about $300 US, $250, $300. And they're doing some AR tracking here, so you can see looking at these set of pipes. What they're really trying to measure, though, is so when you look at the pipes, you can see through the wall and see pipes behind the wall, but they're trying to measure the eye blink activity, and they're using eye blink for menu selection. So you can look at a menu and then blink your eyes, and the EEG across the front of the forehead can measure that activity, because that's where you've got obviously muscles that are dealing with eye blinking, and then you can use that for menu selection. So this provides you a way to do a hands-free menu selection. Normally with a HoloLens, you use the clicker, or you might use some dwell-based selection where we use the head pointer and dwell for a long time. So this is a very nice implementation, and you know, with the brain-computer research, there's a lot of research being done in brain-computer interfaces, and quite a large number in the, or growing number in the AR/VR space. Not so much in the AR space, but the VR space. Quite a number of people, because of course when you're wearing an AR headset, you've got webbing and you've got the head-mount display where you can mount electrodes onto it. What we've been interested in, though, is the other 2 areas of cognitive monitoring and then also the brain synchronization. So I'll talk about both of those, and it turns out there's been much less work done in that space. So first of all, many of you are familiar, of course, with virtual reality training. So here's an example of a training system that's developed to train people how to use the helicopter hoist for a search and rescue helicopter. So it's very difficult and expensive and dangerous to train with that in the real life. But with this system, you can go into VR and you can train and practice over and over again, different conditions like bad weather and so forth. So it's a typical system. So there are many different training systems, and sometimes in those systems, they will change the training environment dependent upon task performance or test performance or some sort of subjective measures. So you do a training exercise based on how well you performed, then the next time you do that exercise, they'll change the parameters. But none of these measure users' mental activity or cognitive load during the task. So oftentimes, you know, at the end of the task, ask you how difficult it was or give you a test, but not during the task. And as I said before, people have started to use EEG with VR. So here's one example of EEG for locomotion. So you can wear the EEG headset, and as you concentrate, you can navigate through the virtual environment. And on the right-hand side, in this case, it's a driving simulator, and then as you're driving, they measure your cognitive load. But in this case, they don't adapt the situation. So VR tools have been shown to be very effective for training, and skills you learn in VR you can transfer to the real world. And some early use studies in VR and EEG, as I said before, has been for interaction or measurement of stress. But in most cases, the VR environments didn't change based upon your cognitive ability. So our motivation for doing this was to build a VR training system that adapted in real time to the user's cognitive load and produced the best performance gain. So the basic idea is that when you're training, if the task is too easy, then you probably won't learn anything. And if the task is too hard, then you'll probably give up and also not learn anything. So what you want to do is tune the complexity of the task to be challenging but not too challenging, and hopefully by doing that enable the person to learn as quickly as possible because it's at their peak learning environment. So we think that we're one of the first people to explore real-time adaptive VR training using a workload that's calculated from the EEG while the person's in the VR environment. So I'll give you an example of that, and this is quite early research, but hopefully it'll show you what could be done in the future. So this is a system we built together. We used this 16-channel EEG headset, but actually from that we only used 6 electrodes. It turns out wearing a kind of professional quality EEG headset with a Vive, you have problems with the straps in the way of the electrodes. So we took some electrodes off. We can then take the raw EEG data and put it into a very popular piece of software called OpenVibe. OpenVibe is basically a visual programming tool for EEG. So you take the raw EEG data, you can use visual programming to process the data and look for certain patterns or triggers in the data. And then we could live stream the output from that into Unity, into the VR, and also we had a system to record and save what was done as well. So that's kind of the basic setup. And what we did first of all is we had to measure people's innate cognitive ability. So some people have higher or lower capacity for workload. So we did that by using a standard test which is called an NBAC task. Many of you may be familiar with it, but you see numbers on the screen, and like if you're doing a 1-back task, if you see number 1 on the screen, then the next number might be number 2. You have to recall the number that you saw just before. And if you do a 2-back task, you have to record 2 before. So it's a memory task, and it gets more complicated the further back you have to remember. So once you get to having to remember 4 or 5 numbers before what the current number is, it's very complicated. So we measured this, and we measured the alpha activity in those 6 electrodes, and that let you establish a baseline for people's cognitive load ability. And then in the experimental task, once we've got that baseline, when people's load that was measured during the task went above the baseline, we would decrease the difficulty of their task, and when it was below the baseline, we'd increase the difficulty of the task. And what the goal was as quick as possible to get to your maximum cognitive capacity and keep it at that level, which we thought was the optimal level for training. So this is the task that we did. So as I said, the idea was to increase the complexity. So we had a relatively simple task, which was target selection. So you can see on these images here, there's a pink box. Inside, and this is what you saw in the VR headset. Inside the pink box, there's, in this case, a yellow sphere. So the idea was, as quick as possible, to find the yellow sphere in the virtual environment, look at it, and pull the trigger on the Vive controller. And then as you went up in levels, it got more and more complicated. So on the right-hand side, there's a yellow pyramid in the pink box, and you can see there's one on the screen. Actually, there's 2 pyramids in the scene. There's one to the left as well. And by the time you got to that level, you had many objects, maybe 30 or 40 target objects, and they were starting to move around, and they're all different size. And you had to very quickly try and select all the ones of the same type before it automatically changed to the next target. So it was very, very difficult. So the target selection was based on different types of objects and colors, and there was shapes and movement as well. So this is the basic task. And this is the task that you might want to use, for example, for training a soldier, how to do very fast target selection and train them on the eye scanning patterns or other types of target selection tasks. So this is a video of it working. You can see the left-hand side, this is the low difficulty. The person's trying to find objects as quick as they can, and they position the reticle over the object and pull the trigger on the handheld controller. And this is the more complicated one. Now that they're trying to find in this case now, all the green squares before they disappear. Now it's all the yellow squares, and you can see it's much more complicated. The VR environment is really simple, and we confine the VR environment to be in the front part of the visual field. So we don't want people to move their head a lot all around, because that will also introduce noise into the EEG signal. So that's the task. And this is the experiment design. Basically, 14 people, didn't have any experience with VR. We measured the response time and then most importantly the brain activity with the alpha level, which measures your stress level. And then we had a 5-minute fixed trial time. People had to try and do this as much as they could in 5 minutes. And as I said before, this is what you typically saw. So here's the time across the bottom. When we started, the complexity level was like about 3. This dotted line is that baseline. And when people hit that baseline, that showed us that they're working at a maximum cognitive capacity. And so when they went above that, then we would decrease the complexity. So we, once you start at the beginning, the task isn't very complicated, and we would quickly, as fast as possible, keep on increasing the level of complexity until you hit the baseline, and then we would go up and down just 1 or 2 to try and keep you at that level. And as I said, the goal was to try and keep you at that level as long as possible, because we thought that was the level that you'd get the maximum number of training. So for each individual person, that baseline was different depending upon their end-back performance. So some people had very good cognitive capacity, and that would be higher. Some people had less cognitive capacity, and that would be lower. So that's the task. This is the response time. This is the increasing levels based in 3 bins, basically. So the 3 is the most complicated, 2 is the medium, and 1 is the minimum. And what we found basically is that there was no difference in response time. There's quite a big variance. So statistically, there was no difference. And that's important because what we're showing is that even though we're increasing the complexity, people were still able to perform at the same amount of time. And that's because they developed different strategies to do that. But this is the most interesting thing. So this is the map of brain activity with frequency. So across the bottom here, you see the frequency, and up on the side, you see the brain activity level, and the colors, it's a heat map. So at the easiest level, you're basically seeing a relatively low level of brain activity around the 0.5 frequency, and on the side here, that's the activity level. But you can see the hardest level, you've got a lot more. There's no laser, well, I guess there is. There's no laser pointer here, I don't think. Oh, yes, there is. This little thing here. So you see a cluster of higher activity level here, and when you do the difference level, you see a spot here. So this is showing that people's brains are working a lot harder to achieve that same level of performance. So as I said, you get this significant synchronization or activity in the hardest difficult levels when compared to the easier difficult levels. So essentially the key finding was that even though people had a similar reaction time and were able to perform the same level, there was a significant increase in brain activity showing increased cognitive effort. So we basically developed a task that we can use to dynamically measure people's brain activity even while they've got the same level of performance. So what we've shown from this is that you can build an adaptive AR training task that will increase people's cognitive load without changing task performance. And we think it's one of the first demos of the use of real-time EEG signals to adapt the complexity of the task. But there's a lot of future work that's been done. I mean, the task we've got is a very simple task, so we want to increase the task complexity. We want to also use this to be able to predict people's performance. So if we can use this task to measure people's cognitive load in the VR, we might be able to predict their performance in the real world. We're also quite interested in using an AR display, because in an AR display, of course, you're seeing the real world at the same time, and there are many more distractors that might happen as well. So this was one of our first experiments. Now I'm going to talk about the brain synchronization work, and this is actually much more early work. So I can show you, I'll talk about the concept, and I'll show you some early results, but we're just really at the beginning of this. And this, I think, is a lot more exciting, and as far as I'm aware, again, we're the only people who so far are working in this space. So the basic question is, can my thoughts influence your thoughts? So if we're both in the same room together and we're doing the same task, will my brain activity somehow magically influence your brain activity? And it sounds like some sort of hand-wavy magic, but actually people have started to study this. So there's a technique used called hyperscanning, and hyperscanning basically means the simultaneous acquisition of neural activity from 2 people. And until recently, this was very difficult to do because the equipment was very expensive. You know, if you wanted to use EEG 20 years ago, you had to spend $25,000 or $50,000 to buy an EEG system, and you certainly couldn't afford 2 systems. So the main idea of hyperscanning is to study how 2 or more people can interact in a cooperative or competitive scenario. So you have this type of thing on the right-hand side here, where you've got 2 people wearing EEG headsets. You capture their EEG and maybe other measures like heart rate, put it into some sort of signal processing, and then you look to see if there's a synchronization between the signals. So this is how you might do it, depending on your budget. If you're really rich, you could have an fRMI machine. An fRMI, many of you may know, lets you image deep inside the brain. But unfortunately, these are going to cost $1 million potentially, and you may not have two of them. So if you're really, really rich, you'll have two of them, and you can put two people on an fMRI machine, you can show them some images, and you can record at the same time the brain activity of those people. If you're moderately rich, you could use an FNIRS system, which they have here. This is where they use infrared light, and they shine infrared into the brain, and you can measure blood flow or blood flow by doing that, and that corresponds to cognitive activity as well. And these systems cost $50,000 a pop or more, and so they've got two of them there. And if you're poor like we are, then you can use the EEG. So here's two people wearing EEG. They've got a barrier between them. They're looking at a display, and both EEG systems are connected to the same PC. And you can buy EEG systems on a variety of price levels. Like I said before, the Muse, which would actually be a very bad system to use for this, but the Muse costs about $300. We've been exploring using systems that range in price from about $1,500 for the Open BCI, which is an open source EEG hardware, to about $7,000 or $8,000. So still expensive, but moderately expensive. So this is the typical setup that we might have for hyperscanning. And then, of course, what you do is you measure the brain activities. And so this shows a frequency of activity from one of the channels on the EEG. So this is the P8 channel. And you can see in the green spectrum, or green region here, it looks like the blue signal is from one person, the black from another person. So in this spectrum here, well, this time it looks like there's some synchronization happening. In this orange one here, it looks like they're not synchronized. And you can measure the phase. You can use some signal processing to extract the phase, and by doing that you can see whether they're in sync or not. So here the phase is fairly well lined up. Here you can see there's a lot of difference in some of the black here, so there's no synchronization. This is from this paper here. So this gives you an example. Here's two people playing music on the violin. They're playing the same song, and so they're both wearing EEG headsets. This is their brain activity from the headsets. So you can see actually the red levels are about the same. So they're playing the same piece of music. They've got the same activity in mind, and by doing that, there's some brain synchronization happening in their brains. So indeed, when people perform a collaborative task, depending on the task, and there could be synchronization happening. Here's the counterexample. So here's two violinists who are playing very different pieces of music. And you'll see now the brain activity is not synchronized as well. So this is an example in music, but it turns out there have been many other studies. So brain synchronization studies and hyperscanning has only been really studied since about 2002, was the first paper came, and there's been about 140 research papers published since then, which actually isn't very much at all. So it's possible, in an afternoon to download all those papers and start scanning through. This is a really excellent paper to read that provides a summary of those papers. And the most important thing for us, though, is that there's no research at all yet done in AR and VR, which I found quite surprising. So in our lab, we're the first ones in the world to start looking at using AR and VR for brain synchronization. So in this research paper, it's a really excellent summary, and they summarize the different types of experiments people have done. So they generally fall into 6 categories. So one is an imitation task. So I'll be sitting across from you in the real world, and I start waving my hand around, and like my right hand, and you put your left hand next to my right hand, not touching it, but you follow my hand. So we're both tracing each other's fingertips. So that's an imitation task. A coordination task might be where we are tapping fingers together, or actually this happens in the real world. When you start walking with somebody, oftentimes your footsteps start synchronizing, and you find that you fall in step with them without consciously thinking about that. There's eye contact or gaze tasks where we have to try and track each other's eyes. People have also done economic games, so they have a prisoner's dilemma or a trust game. So the prisoner's dilemma is very famous in psychology, where you're supposed to either agree or disagree with your confederate and say whether they're telling the truth or not. Cooperation tasks where you're trying to, two of you together are trying to search around and find the same objects. And interaction in natural scenarios, just daily life. So the ones I put check marks beside, these are the ones that are probably good to use in AR and VR. So for example, it's not a really good idea necessarily to use economic game in AR or VR because there's no real spatial interaction, but an imitation task or a coordination task may be better. So this is what's been done before. I better speed up a little bit. Here's an example of that. These two people doing an economic task. So they have to do, they're basically trying to agree on how much money to give each other. So they sit across the table. There's two conditions. One condition is they can see each other. The second condition, they can't see each other, but they can see a monitor, and on the monitor it tells how much money they're exchanging. So, and then you can see the brain activity on the right-hand side there. And the basic story from this one is that when they can see each other, their brain synchronization happens much higher level than when they can't see each other. So there's some cues happening from our face or eyes or other nonverbal things that help us synchronize our brains up. You can see on the right little bar chart there, it talks about you have to self-report on how coherent you felt you were, and the red is when you can see each other, the green is when you can't, and generally the red is much higher than when you can't across the different channels you're measuring. So there's some benefits from doing that. When that brain synchronization happens, people feel like they're more in this flow state. They feel like they're more easy to collaborate with each other. They trust each other better. They feel more sense of social presence. So the idea is that if you can get into this flow state, it will improve your interpersonal communication and collaboration. So we decided we wanted to try and explore this. And so, as I said, this is just very, very early results. We're still running the tests pretty much as I speak. So what we did is a finger tracking task. So you can see two people here, both wearing EEG headsets. And they do several things. First of all, they point at each other's fingers without moving. Then secondly, one of them is designated as the leader, the other one is the follower. The leader moves their hand around and the follower tries to follow. And then after that, they stop moving and they point again with their fingers at each other. So there's three kind of phases as it shows on the right-hand side. And they track off. And this is a repetition of another relatively famous paper that talks about brain synchronization with finger tracking. So here's the results. This is when the people are just pointing their fingers at each other. So, this basically shows the black dots as the location of electrodes on the head, and the colors show the activity of the brain. And then we have people moving the fingers, and these arches here show when two electrodes are in sync. So you can see the person on the left, he's got a couple of electrodes that are syncing up for some reason. The person on the right, nothing much is happening. And then the third phase, as I said, was you stopped and you pointed your fingers at each other, and then you also, and you're not, the important thing in this case, you're not moving at all. You're just holding the fingers, looking at the person. And we found this. So you can see in this case, there's a lot of synchronization happening between the brains, even though the people aren't moving and they're just trying to hold their fingers still. So we were able to reproduce the same results as what they did in the paper, which is very exciting. And what we're doing now is trying to look at how this can be done inside VR. So in VR, so you can see we've got two people here sitting. This is using the OpenBCI system, which is basically a 3D printed electrode set on their head. So we've got two people in the top corner doing this in the real world here. Then we put people into VR. Now the most exciting thing about VR is that you can change your perspective. So in VR, first of all, so we want to try and reproduce the face-to-face task, and we want to look at how potentially AR and VR can be used to enhance brain synchronization by changing perspective. So first of all, here's the VR task. You can see the person on the left and right, and this is the external view. This is the view of the person. So they're trying to move their fingers together. So it's pretty much reproducing what happens in the real world. But imagine, because you're in VR, what happens when you take your virtual body and put it inside the other person's body. And now, because you're inside the other person's body, when you start doing the hand movement task, you see the hand of the other person, you see your hand exactly overlaid on their hand, which potentially make it easier to synchronize. So this is when that happens. So you can see now you're inside the other person's body, and one person has the dark gray hand, the other person has the white hand. And so I don't have results to show from this, but our theory is that when this happens, the brain synchronization will increase, because now you feel like you're seeing the same perceptual cues, you're in the same virtual body, and we're actually recording data from this week and next week. So if AWB had been a week later, I'd have a more exciting talk to talk about. So that's what we're trying to do, and we think, and this is, as I said, this is the first time we believe anybody's done brain synchronization studies in either AR or VR, and what we're hoping is that we can use VR to increase that synchronization, and also AR as well. Running out of time, we're also making a mathematical model of it. So this is basically a spiking neural network that we've developed with our partners to simulate the brain performance. And what we do is we take the raw EEG data, create a network of spikes to pass through our neural network, and then simulate the output and see if we can then have the output from the neural network model that matches the real situation. These aren't so important, but this shows the simulated activity before the tracking, after the tracking. But the most important thing is this thing here. And we have this percentage score on the right-hand side. This percentage score is a percentage that the brain activity is different from the two simulated brains. So on the top one, it says that the brains are 80% different, and this is before we started the finger tracking task. The bottom one is after the finger tracking task, and the same as that picture showed you before, thought Archer's going before. And this shows now the brains are only 60% different. So our simulation is showing that we've got a 20% synchronization happening that's reduced the difference in the brains. And I've got 30 seconds left, so let me do a bit of conclusion. So I think there's a lot of opportunity for EEG use in AR and VR. Most people are working in the brain-computer interaction space, and there's a talk earlier today that talked about that, and there are a variety of headsets in the show floor showing this. But there's also a lot of opportunity for cognitive modeling and enhancing collaboration in many directions for future research. One of the areas we're particularly interested in is what about simulated synchronization? So if you're interacting with a virtual character, and there's a company in New Zealand that, called Soul Machine that builds a virtual character, and most importantly, they simulate the brain activity. So if we're interacting with a virtual character and we can simulate the brain activity, what happens if we take the real EEG signal from a real person and make the brain activity of the virtual character synchronize with you? Are you going to then feel more connected with that virtual character, trust them more, or interact with them better? And overall, at AWE, you've seen a lot of advances in different display technology and capture systems and digital interaction, eye tracking, and in this case, emotion sensing and sharing. All this feeds together into what our lab is researching, which we could call Empathic Tele-Existence, with the idea that you move from being an observer to an activity to being a participant and a sharer. So as I've shown with the VR example, we can put two virtual bodies together, and now both people feel like they're moving their hands at the same time. And that changes your nature of your collaboration. So that's what we're doing. We'd love to have some collaborations, and if you're interested in collaborating with us, please email me or send me a message on Twitter, visit our website, and if you want copies of these slides, email me and I'll give you all the copies of the slides as well with the videos. Of course, you can watch the video on YouTube too, but I'm happy to give you all the material. So thank you very much for your time. I'm not sure we're 2 minutes over. I'm not sure if we've got time for questions or...